Greetings and welcome to my new calculus channel. My name is John Gabriel. And today I'm going to be discussing definition 4 of Euclid's elements in book 5. So you'll recall that we discussed definition 3 in the previous video, and I'll go over that before I do definition 4. So let's begin. Now, definition 3 was the definition of a ratio. And remember, I talked to you about quotientness. In other words, you can take any two magnitudes and form a ratio from them, but they only have a relationship if each of those magnitudes can be measured by a common divisor or by each other, okay? So that is what quotientness means. And the Greek word pilikotita means quotientness. There isn't actually an equivalent English word. I think perhaps the closest is that they have a relationship that they're divisible by a common magnitude and provided that they're not the same magnitudes, okay? Excuse me. So they're different magnitudes, but they're measured by another common magnitude. Okay, so that was definition 3. So now definition 4 states the following. It says, these magnitudes are said to have a ratio with respect to one another, which when they're multiplied or being multiplied are capable of exceeding one another. And I'll tell you, I was stumped on this for a very long time. In fact, for several decades, because I couldn't really understand what was being said here, what Euclid was trying to say. But this follows logically on definition 3, which says, okay, well, so we now have a ratio, and let's see what kind of ratios we can have. And so definition 4 discusses a specific kind of ratio, and it's the ratio which basically tells you that if you have magnitudes that are smaller than this pink chosen unit, like that, and you multiply them, then the result, which is a red line, will never exceed any of them, okay? But if the magnitudes are greater than the chosen unit, then the product of the two, green and blue, has a product of red. The product of red will exceed both of them. So we'd call this a special ratio where the product of these two magnitudes, the blue and the green, have a multiple, red, that exceeds both of them. Okay? So, now, I don't agree with Thomas Heath's interpretation or anyone else's that I have come to know. But one of the most laughable is the one by that cranky Professor David Joyce of Clark University. So, he writes this on his site. He says, this definition limits the existence of ratios to comparable magnitudes of the same kind, where comparable means each, when multiplied, can exceed the other. And he says the ratio doesn't exist when one magnitude is so small or the other so large that no multiple of the one can exceed the other. Well, and the funniest part is this. He says, this definition excludes the ratio of a finite straight line to an infinite straight line, and the ratio of an infinitesimal straight line, should any exist, to a finite straight line. So, I mean, it's just so laughable that a professor of mathematics can say something like this. Shows you how clueless he is. And his site is actually one of the better sites on Euclid's elements. But he's talking here about infinity and infinitesimals. And, of course, all these things were totally rejected by Euclid and the ancient Greeks. In classical Greece, infinity was an anathema concept. And in my mind, it's still an anathema concept, and I consider myself the greatest mathematician alive today. So that is just absolute garbage. And of course, the ancient Greeks rejected any ill-formed concept. So the only numbers they recognized were those called rational numbers. And by the way, it's kind of silly to say rational number, because rational is redundant. If it's a number, it is rational. That's basically, in order to be a number, it has to be rational. So irrational magnitudes were never called numbers of any kind, by the way. You don't find any expression such as irrational number anywhere in the Book of Elements. It's always an irrational magnitude, meaning they have no measure, okay? So as I've said, magnitudes in such a ratio are greater than the chosen or standard magnitude of measure. So if you had to choose a measure like that, and these two measures are less than this standard unit, then obviously the product will never exceed any of them. But if you go above it, above the 2 units like that, then this product will exceed product will exceed both their line lengths. Okay, so even if they were just 2 like that, and this here is the only case, well, actually you have to be very careful here, because this here is not 2, it's actually 1, because we've chosen this as the chosen unit. Okay, so theoretically we would be looking at something like this. Okay, all right, so now let's look at the simple version. Euclid is talking about magnitudes greater than the lowest common divisor, or the unit magnitude, whatever it might be, in the process of measure. So, for example, the magnitudes 2/10 and 8/10 do not qualify, since their product 4/25 is less than both of them, right? Also, 0.8 and 3 have a product of 2.4, meaning that neither 0.8 or 3 can be in such a ratio. Whoa, you may say, Mr. Gabriel, what you used are numbers, but magnitudes are not numbers. You'd be dead right. But I used that to, instead of coming back here and showing you in this context, that in terms of a chosen or a standard magnitude of measure, that's what it means. Okay, so all I've done here is I've assumed the abstract unit 1 in this example. Okay, so and also it helps to illustrate the fact multiplication in geometry, as you've seen over here, only uses magnitudes. Okay, right, and they may have a number. They may have a number that describes them, or they may not. Right. So, for example, if you've got something like let's say, let's do this. Let's make it something slightly like, say, about there. That could easily be the ratio that is realized for pi, right? Almost 3 point something to the unit 1. So the ratio P colon Q literally means P compared with Q. And if P can be measured by Q and or other parts of Q, then the number P over Q describes a measure of P. P is the antecedent in the ratio. Q is the consequent. Okay, and this expression does not mean P divided by Q. It is merely a name that identifies the measure of P by Q. Okay, and proposition 12, one of the most important, is the one that will realize all the 4 arithmetic operations. Okay, and I'm not going to go into that now, perhaps another video. But this proposition establishes all the arithmetic, which is eventually transferred to algebra through the abstract unit. If you're not already a subscriber, become one, okay? And click like so that others can learn of this wonderful knowledge. Remember, I have many enemies, and many of them come on here and they simply vote my videos down because they do not like me or my ideas. So, I'm John Gabriel. This is a New Calculus channel. Till next time, goodbye.